Morning everyone, and welcome back to the third session of the GTS webinar series. Thanks again for participating, thanks again for registering. Good to see a lot of people coming back for a bit more of these sessions. And if you're joining us for the first time, welcome to you guys as well. I think we've had a lot of good feedback over the last couple of weeks with regards to the session. So if you are just joining us for the first time today, you are able to get a recording of the previous sessions. Maybe just contact us, one of your representatives, or just Josh or I directly. And we'll be able to send you a link to those recordings. So as you know, I'll just do the same introduction I've done previously. These are educational webinars, not meant to be product pushes or anything like that. It's really educational sessions that we're wanting to run through the winter months. And just have short, sharp sessions. So 11:30 on a Thursday, it goes for 35, sort of 40 minutes. And just we'll have different speakers each week, talking on different topics, hopefully interesting topics that are of note to you guys, and you get something out of it. So again, just to reiterate, being a webinar format, it's sort of one-way traffic where we do the presentation while everyone else is on mute. If you have any questions, that's certainly fine. We do encourage that. The best way to handle this is to click on your chat button within your menu, within the Zoom meeting menu there. There should be a chat button. You can click on that chat button, type your question in there, and then we'll handle those probably at the end of the session. So at the end of the session, we'll have a Q&A, and we can go through those questions and answer those as we go. So, today we have none other than an industry icon, Peter Kirby. Peter Kirby running the session today. If anyone knows Peter, you'll know that he's a wealth of knowledge on everything turf management. And in the last year, he's been pretty busy. He's been running his own business called Indigo Specialty Products. That's a business that he's operating to develop a lot of unique turf maintenance products and bring those to the industry, ones that have a sort of certain fit in the industry. And as part of this development, Peter has been doing a lot of research and trial work on surfactants, looking at how they work, how they achieve certain turf management objectives with regards to root zone moisture. So he's been looking at a lot of chemistries, how they work, how to blend them, how to put them together, and how to get results basically in our climate. So that's why we thought we'd get Peter on today. He's going to delve into the chemistries of soil surfactants, maybe debunk a few of the muck and mystery around them, and he'll look at what the differences are in the chemistries, and then how those differences affect how they work. So hopefully that's going to be of some value, get something out of it, and nothing more to do. I'll hand over to Peter now.
Thanks, Paul. Thanks for the opportunity to GTS to talk today. I appreciate everyone's time as well. I know you're always busy, even though it's a bit cooler at the moment. But I guess today is really, as Paul suggested, I'm looking at soil surfactant chemistries, just generally the ones that are common in the industry, how they work, and basically how they perform in certain conditions. And then I'll also just briefly at the start just touch on soil hydrophobicity. How it occurs, just briefly. I know I've only got 35 minutes, so I've got a time frame that I need to stick to. So I'll try and get through the first bit fairly quickly, and then we'll delve into the actual surfactant concentrations or formulations. Okay, so the first slide's really just what causes soil hydrophobicity. So there's a number of factors. Obviously, they're all the biggest one and the most common one is breakdown of thatch, organic matter breakdown from thatch decomposition, which obviously releases sort of biological materials which are quite complex in structure, and they basically actually go into a gaseous phase, and as they cool, they solidify and basically stick on the soil particles. So they're actually non-polar surfaces which are very hydrophobic, and so that's probably the biggest cause. As we know, fungal basidiomycete fungi like fairy ring are obviously and generally a lot of of that fungal group are quite hydrophobic in nature. So you can see down the slide there, just some droplets of, this is actually a plug taken out of a fairy ring. And you can see there it's quite hydrophobic in nature. Obviously water's quite not penetrating at all due to that hydrophobic nature of fungi. Other microbial activity groups like actinomycetes are also, their activity generally produces an exudate, which coats soil particles, makes it hydrophobic. So pretty much most things in the growing system, as they decompose, will add to organic matter, which then adds to hydrophobic situations. One of the big things, and a lot of research in soil surfactant technology in recent years, has been around wildfires. Obviously, with the wildfires we had over summer at the end of last year, there's a lot of work being done around eucalyptus. As eucalyptus trees actually combust, they actually release a gas which then penetrates through the soil and coats soil particles to become extremely hydrophobic as well. So there's a number of factors which create that organic coating, and basically the key to remember is it's a non-polar molecule, which means water finds it is very difficult to penetrate. So this is just a picture from Keith Carnock at University of Georgia. So this is just a soil particle, and you can see there, obviously a standard soil particle with no organic coating on it. Nothing really, looks a bit like a mountain, but it's basically just a pure, sand particle. And then you can see there on the right hand side, the organic particle with the organic coating. Sorry, the sand particle with the organic coatings on it. And you can see there that's a non-polar surface. Water can't penetrate. It's very hydrophobic. Obviously, when water hits that, you can imagine it just sort of bouncing off and sort of moving back into the pore space around it. So these concentrations can take quite some time to build up. But as I said before, everything in the turf management system is actually adding to that organic sort of coating as it decomposes and breaks down. Okay, so what are the major impacts of soil hydrophobicity? Obviously, poor infiltration into the soil environment is probably the biggest thing. As a result of that, water sits on the surface for extended periods of time, which increases its time for evaporation to occur. If we lose it to evaporation, obviously, it won't have any impact on, it won't have any benefit for turf management. Water flows, like preferential flow. So water really flows, takes the easiest sort of path, or the least path of resistance to. So, if it'll find a channel and it'll move. So the thing with preferential flow is that it basically, we get wetting that's not uniform whatsoever. So you can see here on the next slide, we've got preferential flow occurring. Water's moving down in the least at least channel where it can move through without, going around hydrophobic areas. As a result, you can imagine in that situation with fungicides, insecticides, all those sort of things, we get massive losses. Nutrient-wise, you're getting major losses in that situation because water's flowing through those areas and not actually sticking, sort of staying where we need it around the root zone in the turf environment. So localized, as a result of that preferential flow, then we get localized dry spot development. So localized dry spots are just purely, just lack of water for the plant. Water, if the soil's hydrophobic, the soil can't wet. As a result, turf wilts and eventually turns brown. In those situations, no nutrient availability is, nutrient can't go into the plant because it needs to go through via water. Chemical inputs and everything, other input in the turf management system can't be uptaken. So as a result, the plant, wilts, falls away, no moisture, dehydrates, falls apart. And then some of the research findings, just in general, that localized dry spot can cause is, obviously increased erosion, poor seedling establishment, obviously non-uniform turf growth because we're just not getting good movement of inputs uniformly through the profile, reduced irrigation efficiency. Obviously, we're getting, surface runoff, and losses to evaporation. We're getting water moving through channels through the soil profile, not sort of uniformly, so we lose it drains and leaches more readily, and as I said before, we lose our pesticide and fertilizer inputs as well in large concentrations. So obviously, the whole purpose of using surfactants is to try and get that turf system working more efficiently again and get better uniformity across that whole growing environment, therefore making everything that we put into the turf management system better available to the plant, so therefore we get a better response from turf growth. Okay, so I guess this is just another slide looking at, I guess, the same thing from the last slide, but in a real turf situation. So you can see there, this is a soil column treated with water. Obviously, this is a hydrophobic material, and you can see there again those preferential flows. Nothing's going through uniformly. We're getting channels forming, and we're getting losses of everything that we put into the turf system, because it's draining through in certain areas, but not across the whole. Not uniformly across the whole growing environment. On the right-hand side, again, this is treated with a wetting agent. You can see there, obviously, a good uniform wetting front, so it's moving down, it's penetrating through the soil uniformly, and obviously we're getting good initial infiltration into the soil environment. Therefore, we're getting reduced losses from evaporation and evapotranspiration. Okay, so how do soil surfactants work? So there's two main areas. One is reduction in water cohesion, which I'll talk about, and the other one is sort of molecular polar bonding, which I'll talk a bit about. Sounds like a major thing, but yeah, it's not that complex, I guess. Okay, so I just wanted to first start by sort of explaining what the general structure of a soil surfactant looks like. So one thing to point out initially is that soil surfactants are basically amphiphilic with compounds. So they basically contain a hydrophobic or a non-polar end and a hydrophilic end, which is a polar end. So we'll talk about polarity a bit in a few minutes, but essentially it's important to note that this polar end is a water loving. So it interacts with water, it interacts with the hydrogen bonds in water, and basically holds water on it. And then we have this whole hydrophobic end, which basically it has no interaction with water whatsoever. It actually repels water, but it actually attacks or touches the non-polar surfaces, so like organic coatings on soil particles. Okay, so the first means of surfactant mode of action is really its reduction in water cohesion and surface tension. So basically, water it's called H2O for a reason, obviously. So it's got two hydrogen bonds or two hydrogen atoms or molecules, sorry, and oxygen molecule, which are bonded together. The thing with water is it actually it likes its own company, I guess, in that basically because it does have a hydrogen, it's got two hydrogens extending off the oxygen. These two hydrogens bond to other oxygens. So therefore we get all this surface tension or cohesive forces pulling water droplets together. So if you look at water on a surface which is impermeable, the water will bead like this here, and therefore pulling, it's basically, and that's all the cohesive forces that water has, pulling it together, making bigger droplets. It likes to spend time with each other. It actually enjoys its own company. So it pulls water to it and sort of beads and creates that sort of beading that we see when we wash our car or something like that. Those cohesive forces, sort of really stop water from sort of penetrating into soil environments or through thatch and through leaf materials, because it sits there. It bounces on the leaf and sits. It doesn't actually sort of go through the leaf or go through the thatch efficiently when it's in big droplet sizes like that. So what surfactants are really good at is breaking down those cohesive forces. So as you can see on the right hand side, once we apply a soil surfactant to a water droplet, the hydrophilic ends, or the water-loving ends, go straight into the water and bond with those hydrogen ions, and basically remove the attraction for the water, sort of those cohesive forces pulling itself in, and it starts to then interact with the hydrophilic or the water-loving end of the actual surfactant molecule. And as a result, it reduces the surface tension, breaks down those cohesive forces, and then shears droplets up. So it makes lots of small droplets out of the bigger droplet, which then become much more easy to then penetrate and move through that thatch layer into the soil environment. So one of the key functions of wetting agents in general is just purely just making water droplets wetter, to be honest, and basically making bigger droplets smaller so they can easily get into the soil environment. And the key, once it's in the soil environment, obviously the smaller the droplet size, the easier it finds to penetrate through pore spacing and move, into the soil environment as well. So that's really the first part of a wetting agent, is just basically having that, getting that smaller water droplet occurring, so therefore we can get better penetration. Okay, so the next one's a little bit more complex. So as I explained before, this is a different way of looking at a surfactant molecule, but again, nothing changes. We've got a water-loving end, which obviously water is attracted to. So the hydrogen bonds, it forms weak bonds, onto this molecule, and then it has basically a hydrophobic end or a non-polar end. So as I said before, these hydrophobic coatings that coat the soil from that decomposition of organic materials are basically a non-polar as well. So basically, in the law of chemistry, polar likes to basically attract to other polar materials, and non-polar materials attract to non-polar materials. So basically, this hydrophobic end on the surfactant molecule will basically bind to the hydrophobic coating on the soil particle. So therefore, it basically binds onto that organic material. The actual hydrophilic end, or the water-loving end, sticks out into pore spacing, and then when water comes through, it basically drops and it forms hydrogen bonds with these hydrophilic ends of the surfactant molecule. And the good thing is it's a relatively weak bond, which means that then when roots go in and need water, they can actually extract water from that pore spacing quite efficiently. If it was too strong a bond, water would never actually leave that bond, and therefore it would never be available to the plant. So the good thing is it's a fairly weak bond because it's hydrogen. Hydrogen doesn't have a high molecular weight, and it can easily sort of let that water go, for plant uptake. Okay, so that's pretty much, I guess the first, that's, in a nutshell, how, water or how, surfactants sort of bind to organic materials and basically hold water around soil particles that are hydrophobic in nature. So you can imagine when, you put a lot of surfactant into the soil environment, you get this situation where you've got all these molecules hanging out into pore spacing. So this is pore spacing through here. We've got the organic coatings on the soil particles, and water's basically coming in and basically hitting those molecules that are extending out into pore space, and that's how it holds water. Obviously, over time, this organic coating, it's actually, the organic coating itself actually is polar and non-polar in its own right. So it forms over the particle, and it's non-polar on the outside. But once you get water in underneath that organic coating, it's actually got a polar side to it that's on the inside of on the soil surface or under the soil surface. So basically, as we sort of overweight these areas with a lot of molecule, that organic coating starts to break up, and therefore we overcome that hydrophobic nature of that soil environment, and we put water in, and obviously we start to hold a lot more water throughout that soil profile. Basically that, by doing this, we ensure that uniform infiltration that we're looking for, and that, good soil wetting, for over a period of time. Okay, so one thing to point out though is that, what we just went through was a fairly basic surfactant molecule. I guess not all salt surfactants are the same. So, a lot of people say that they're all dishwashing detergents, but they're all very different in their makeup and basically chemistry. So I'll run through the purpose of today is to run through each of these key chemistries and how they interact with the soil and the water. Yeah, I guess one thing to point out is, these are all different molecular structures that we can use in soil surfactants. And they all vary in several ways. One is obviously their structure. So you can see there, their structures look very different, and I'll explain each of those. The molecular weight's different. So obviously the molecular weight's extremely important in terms of how long it's going to stay in the soil environment for. Microbes they've all got a carbon base to them. So essentially they will get broken down over a period of time and by microbial activity. But yeah, the higher the molecular weight, obviously the longer the product persists in the soil environment and takes microbials to break it down properly. There's obviously different charges. So we've got non-ionic surfactants, which are probably the majority of the surfactant market nowadays. The cationic surfactants, which I won't talk too much about those. They really haven't ever been used in the turf market in any big way. However, things like algae fix, benzalkonium chlorides, a lot of those products are cationic materials, which they've got more biocidal activity. Anionic surfactants, I'll go through some of those. They have different properties to. They're quite efficient wetters, but they have some soil dispersion activity, which isn't always ideal. The hydrophobic chain length can be very different. As you can see there, these ones have, these ones are actually quite small chains. These are actually, in perspective, are actually quite bigger chains. And yeah, so the variation in those can be quite a lot. The attachment points and the way the actual surfactant sits on those non-polar surfaces can be very different as well. So I'll go through that again. But I think the key to point out from this slide is that how they are constructed very much determines how the product performs in the soil environment. Okay, so just really looking, I just wanted to give you sort of a bit of a history, I guess, in terms of the development of surfactants. So, the initial work in agriculture and turf really started with surfactants around 1954. So we actually had, that's when they started finding that they saw benefits of using surfactant chemistry to really improve water processes in the soil. So, very early days, the original products, which I'll go through some examples in the next slide, but polyoxyethylene is a molecule that first came to market, and they had non-phenyl ethoxylates and anionics in around that period as well. So all very early days, not really understanding totally how they interact with the soil, but they found that they, giving significant penetration benefits. Some of those are very short-lived, so they only work for a short period of time. But I guess the key is that they were doing better than just applying water and putting up with hydrophobic soils. Then we sort of look in 1992, the first, I guess, non-ionic sort of surfactants really came to market. These ones were, the first true non-ionics. These are modified organosilicone ethoxylates. These are things that are used in herbicide activity as well as soil, quick penetrant soil materials, which I'll talk about a bit further. Then 1995, we got reverse block copolymer technology. 96, we got straight block copolymer technology. So this is the one that's in a lot of soil surfactant formulations nowadays. And then we saw 2003, we had humic substances, which redistribution molecules, which basically works on the top few centimetres of soil in removing those organic materials that eventually build and lead to organic coatings. Then 2004, we saw the first modified block copolymer, and then we're seeing subsequent advances in block copolymer technology. And sorry, I missed alkyl polyglycosides in 2000, which is, I'll explain that. So, there's a whole, as an evolution, we still got some of the technology that's been around for quite some time, but we've got newer technology coming through at a regular, sort of period that, improves what we're doing and improves our water processes within the soil environment. Okay, so if we look at exactly what, some of the examples, so anionic blends, very much, some of the AquaAid products, have those anionic blends, stem relief, pervade, there's some products there that people I think would be fairly aware of. Again, there's negatives around the anionics in that they, they do disrupt or disperse, finer soil types, but they, they're very good at moving water through the profile because they're physically moving the soil environment around to move water through. The only problem is if you want to hold moisture, they're not the ideal product for that purpose. You've got your POEs and your MPE surfactants or non-phenol ethoxylate surfactants. Obviously, there's quite a range of products there that first came to market. The original wetter soil formulation, which I think a lot of people have, I guess, were aware of. It was certainly one that I was aware of when it first came into the industry. It was sort of in that group. AquaGrow is another one, that we brought in, that was brought to the market quite some time ago. Cationic surfactants, as I said, they're more biocidal. They don't have so much activity in terms of soil processes within the soil. They also compete for nutrients on soil particles, so they're not really seen as ideal for soil wetting. And then we go to this big group of common chemistry, which it really is, sort of block copolymer technology. So, we have the straight block copolymers, which are very long term. So that's the current wetter soil formulation. The stem and the 90 type products, the products that by agris that really, have quite residual performance in the soil environment. High concentration of active ingredient gives you that residuality. Then we use straight blocks in injectable formulations. Obviously, they have to be diluted in that situation because they're actually quite viscous in material. So we have to bring the concentration down in those situations so that we can actually get it out through an irrigation system. Those products, because we're putting out a less active ingredient, obviously need to be applied more frequently to overcome soil hydrophobicity. Then we go to straight block copolymer technology, shorter term ones. So again, a little bit less than these really highly concentrated block copolymers, but have, basically used on a monthly basis to build levels up in the profile. And then we have reverse block copolymer technology, which I'll talk about more, but that's sort of where a lot of the newer technology being developed now is sort of being aimed at. So although they've been around for quite some time, these products are quite efficient in holding moisture in the soil profile, and I'll explain that a little bit more later. But I guess the key is that if you want something to hold moisture, this group of chemistry is very strong at that. And then, as I explained earlier, modified organosilicones ethoxylate, so that's breakthrough gold, ensure penetrator, quite a number of products. You have organosilicones in their formulations to help get water penetration into the soil environment. Then we have combinations of block and reverse block, so basically putting them both in the formulation to give you, good control of those hydrophobic situations or curative activity, as well as give you extended residual activity or extended moisture holding capacity. And then on top of that, this newer chemistry group that we've got, a blend of block copolymers and newer technology in that APG, which is developed in around 2000, which is a product that reduces surface tension significantly and overcomes those cohesive forces that water droplets have. So, you're looking there at, Dispatch, Broadway, Forte has a blend of those materials in it, plus another surfactant. And then we have this real new technology which is coming to market. So obviously Revolution was the first modified block copolymer, and then we have a new product that we're developing at the moment that is basically a modified block copolymer as well, which I'll explain a bit more. Okay, so I won't spend too much time on these ones. So anionic and I guess blends with anionics, as I said before, extremely fast wetting. They're obviously negatively charged surfactants. They can be phytotoxic to turf if they're left on the leaf. They can cause dispersion on finer soil particles, which can be extremely beneficial in cooler months of the year where we need to pull water through, but they can be very detrimental in really warm conditions where we're trying to hold moisture, because they're actually effectively working on the clay particles and disrupting that clay particle within the soil profile and modifying that environment. So to hold, we start losing moisture holder retention if we use those products in the summer months of the year. And as a result of that, they're not ideal to be used on finer texture soils in those summer months. Obviously introduced in 1954. Okay, the second older chemistry group is the POE, so polyoxyethylene and non-phenyl ethoxylates. Can be very phytotoxic to the plant if left on the leaf, particularly this POE group. So very strong at reducing surface tension and getting water through thatch, but once it hits that soil, it can become quite, it basically, it doesn't overcome hydrophobicity that well, this group. Non-phenyl ethoxylates are very strong in overcoming hydrophobicity, but they're actually got known environmental issues. So they actually stick around too long in the environment, and they've been found in waterways and things like that, many years after the product's been applied. So you've got to be careful using those. If you leave them sit on the leaf, they actually interact with the cuticle quite significantly. And as a result, they can strip the cuticle off the leaf and dry the plant out artificially and create a phytotoxicity as a result. As I said before, they enhance water movement in the soil via reducing that surface tension. Once they get into that soil environment, they don't really bind well to soil particles. They actually, they sort of help water move through the profile. So they're not strong in terms of retaining moisture within the plant, within the soil, sorry. Okay, I'll get modified organosilicones ethoxylates. So again, these are super surfactants. These things are called ultra penetrants. They're very effective at reducing surface tension, that I explained before, and reducing those cohesive forces of water. They're very effective at penetrating hydrophobic turf areas quite quickly. But the negative that they have is that they're short-lived. They've got lower molecular weight. And as a result, you have to reapply frequently to basically keep water moving through those hydrophobic areas. They have low foaming qualities, and they are used in some surfactant formulations just purely in small concentrations to reduce foaming. And as I said before, those things were introduced in the 90s. Okay, so this is now we're sort of into the crux of the technology that's used the most in wetting agents. So block copolymer technology is pretty much a standard in the surfactant industry, and you won't find too many products that don't have some form of block copolymer in them. So they're the most commonly used today. They're introduced in the mid-90s. They're much safer to the plant than anionics and I guess the previous products we've spoken about. They still have some cuticle interaction though, and so making sure you irrigate following application generally does help. Ensure that there's no interaction with the cuticle of the plant. Most of the products are quite residual in this group, so this is your wetter soil type formulations. So they give you quite long residual, high molecular weighted materials, which take time for microbes to break them down. So they work for a period of time. They're very effective, particularly the straight block copolymer at reducing soil repellency. And they have good residual activity, as I said. So there's two basic structures used, the straight block and the reverse block. And so basically these products are formed by mixing ethylene oxide with propylene oxide. So in a straight block copolymer, the ends of the molecule are basically ethylene oxide, and then they have in the middle or the center of the molecule the propylene oxide. So as a result, we've got basically one end of the molecule, which is, non-polar, and then we have two polar ends, which basically provide the arms to sort of reach out into soil, or reach out from soil particles into pore space into hold water. In a reverse block situation, we actually have the opposite. So we actually have the PO ends, sort of the propylene oxide on the ends of the molecule, and then we have an ethylene oxide in the center of the molecule. And what that gives us is greater arms to extend out into soil pore spacing and to hold water. So they have much longer tail on the molecule, which therefore allows it to extend out into pore spacing and hold significant amounts of water. So much more water than a straight block. So as I said, the two structures are there. Straight blocks are mainly used to enhance water movement into the soil environment. So they're very strong at getting water in. They're very strong at reducing surface tension, and then they're very strong at bonding to those organic coatings on soil particles. And as a result of that, when they overweight that organic coating, obviously soil hydrophobicity is sort of broken down over a period of time with the number of applications. Reverse block copolymers, very strong soil moisture retention because they have that hydrophilic chain that extends out into pore spacing. So they're very strong at holding a lot of moisture in the soil environment. So if we in sand profiles in the summer months where we really need moisture retention, reverse block copolymers are the way to go because we can hold a lot of moisture around them. They're not so strong in penetrating hydrophobic soils by themselves though. So as a result of that, we need to use other materials around them to help get penetration into the soil environment. So I think everyone sort of heard of that term matrix flow, and that's really what reverse blocks do with repetitive applications. It builds on the soil colloids, extending out into pore spacing, and we start, really, it actually affects infiltration of water by holding so much water in that pore spacing. So sometimes we can actually oversaturate the profile in using those products. Okay, so that's I guess the older technology. Now to the newer chemistry. I think the first one is this is Revolution. Has patented a variation to a block copolymer. So they basically did that by modifying the methyl caps on the molecule to actually, by putting methyl caps on the molecule, they're hydrophobic. So they actually bind to organic coatings as well. So essentially what happens with methyl cap copolymers is that they actually have 3 attachment points to the hydrophobic or the non-polar soil coatings, and therefore they're actually sort of very close to, they're holding water very close to soil particles, and therefore, providing increased air in pore spacing. So where you've got water, you can't have air. So by holding water closer to the soil particle, we increase porosity, and therefore we talk about those balanced air to water ratios that we've heard mentioned a lot in marketing material around Revolution. So it was introduced in 2004, and really, it's a great product for, using to help sort of, particularly in those cooler months of the year, try and hold water close to the profile, but let water drain through and increase oxygen, most importantly, within the root zone. Okay, I'm running short on time, so I'll quickly hurry up. This is new technology that's another variation of a block copolymer. So this one is only just being researched now, just launched in 2019. This material is basically got it's a modified block copolymer that has, I guess, a large non-polar part of the molecule. So therefore, it's really been geared up to have a really strong absorption to that those non-polar coatings, and basically it has, I guess, smaller hydrophilic heads on it, which hold water close to the soil particles, similar to what Revolution does. But the benefit of this is that with that strong absorption onto those organic coatings, we need, it actually really breaks down that hydrophobic nature of the soil quite well. And because it's got that larger base, it provides less rate, better responsiveness to applications, and really strong, curative activity, as well as good preventative activity of soil hydrophobicity. So that molecule was launched in 2019 in the US, it'll sort of soon be in the Australian market, due to the performance that's been seen in research in Australia. So the last group is alkyl polyglycosides, APG as they're called. These are basically a sugar molecule, reacted with a fatty acid, and they're basically the greener chemistry. And when they're mixed with block copolymer technology, they can provide significant synergistic performance. They're very strong at breaking down those cohesive forces that we spoke about earlier, and they're really good at getting water through the thatch layer to the soil environment, but they're not so strong at actually getting through the soil environment. So that's why we mix it with the block copolymer to enhance that effect. They've got good plant safety, very persistent in the soil. Not very persistent, sorry, breaks down quite quickly, so it needs to be reapplied quite regularly. Being sugar, obviously the microbe activity breaks it down rapidly. Dramatically improves water penetration rates through thatch, but doesn't, sort of very strong and reduces significant amounts of evaporation by moving water off the leaf and making sure that it's getting to the soil environment. Okay, so that's pretty much the core of the technology. I had to rush through it a bit because of the time. I guess I'll just leave you with this. Concentration of surfactant loading is critically important. So, the whole point of putting surfactants out is to basically do the job in the soil environment, but to do that, we need good concentration. So, using materials with really high concentration of surfactant is important to basically ensure that you get the result you require. The ratios of each surfactant chemistry is really where the proprietary information comes in, and where a lot of field trial work needs to occur. You can actually have the wrong proportions of products. So the key is to help when we're selecting surfactants or developing surfactants. We want the products to sort of get through the thatch to the soil environment. Then we want a product to sort of get into the soil environment. Then we want another product to hold water in that soil environment. So, those proportions are critical. And I think the key is to be using or looking at products that are specifically developed and researched for Australian growing conditions, that have been tested in our environment and made sure that they work, for the exact needs that, most of us are looking for. So, and just the last point, all surfactant chemistry has some potential to attach impact on the plant's cuticle. So, obviously irrigation is always really important to make sure the product's off the foliage and in the soil environment. Okay, so I think there's a couple of questions here. I'm just looking at... Sorry, I think we're, I don't think there's too many questions. Is there any questions? Does anyone want to send any questions through?
As we previously mentioned, if you've got any questions, feel free to just contact us anytime. You contact Peter, contact myself. Contact your your local GTS representative. More than happy to answer them. I think after previous sessions, there has been a lot of questions afterwards. Guys have been ringing through and emailing through, and that's fantastic. And we're more than happy to answer the questions that way. So really thank Peter for his time and putting our presentation together. It was, there's a bit of heavy information in there, but I think there's probably three main take-home points from there. I think that there's differences in surfactant chemistries, and those differences really affect the performance and the role they play in turfgrass, root zone moisture management. Even though many wetting agents on the market contain similar chemistries, the way they are formulated, their ratios, and how they're blended really does affect their performance. So they're not all the same in that regard. And really, it's about doing the trial work as well. And Peter's been doing a lot of trial work in Australia, and it's getting those chemistries, putting together and testing them in Australian conditions on our soils, and making sure they're achieving desirable outcomes for the way that Australians, manage turf grass. So the way we irrigate and the way we manage turf grass is going to affect how we, what we want in terms of our soil moisture. So getting those chemistries, putting them together here and testing them out here is, I think, a critical part. So really appreciate Peter's time and all that. So next week, we're going to go a little bit of a different direction. Probably more relevant to the southern states, but if the Queenslanders and northern New South Wales guys want to join in, feel free. But we'll be having, we're looking at a new chemistry in POA control, in vent. It's a new technology on the market. As I said before, this isn't really a product thing, but this, I think, kind of fits into the realm of, like a Primo Max or an Acceloprin or something like that. It's a bit of an industry-changing chemistry, especially for those guys down south. So we're going to have Nadine talking about that chemistry and about that technology, the history, the trial work, how to use it, everything like that. So after that, we've got a few interesting talks, so they'll continue on. So stay tuned, have a look at the links that come through, and anytime if you want a recording of any of these, feel free to grab it. So really appreciate everyone's time. See you next time. Great to have you.